This is our second class on continuous functions. What did we learn in the earlier class? We learned how to check the continuity of f at one particular real number a. We learned how to check if f is continuous at one point. In this class, let us extend our area of concern and we will check if f is continuous on the whole of the real line. How does it behave for any real number? So that is what we will do now. Trust me, it is very easy. Only proving the continuity at one point requires knowledge of limits and all of that. But then once that is done, to prove the continuity of a function in the whole of the real line, that's very easy. You just need to know two things. You need to know the properties of continuous functions and you need to know some examples of continuous functions. Combining those two, we can prove whether f is continuous or not on the whole real line. So let us start with some properties of continuous functions. Now these are the properties of continuous functions. If you take two continuous functions, two functions which are continuous in their common domain, then what do you have? Their sum is continuous, their difference is continuous, their inverse, both of their inverse is continuous. But then remember, not on the whole D. From D, remove those points for which f of x is equal to 0. We cannot have f of x is equal to 0. It will tend towards infinity. So remove the troublemakers, then it will be continuous on D. The same with quotient of two continuous functions. If f and g are continuous, f by g will also be continuous. But remember, not on the whole of D. From D, remove all those x, remove the troublemakers for which g of x is equal to 0. Then f by g is continuous. Alpha f is continuous where alpha is a real number, not a complex number. The product of functions is two continuous functions is continuous. The composition of two continuous functions is continuous. So, if f and g are continuous, then all of these functions will be continuous. Now, before we go on to the examples, let me tell you one thing. Please note the difference between the product of two functions and the composition of two functions. Now, you see, this is the difference. You have a function f which maps every element to 3 into that element plus 7. You have g which maps every element to its sign value. So the product of them will be just this, their product. But then f composition g means what? First you apply g. When you apply g, you map x to its sign x and then you apply f. That means wherever there is x, you are going to put sign x instead. Now g composition f. First apply f. What happens? You map x to 3x plus 7, then you apply g. So this is the difference. Now we go on to the examples of functions. Now these are some examples of continuous functions. The identity function, the constant function, the polynomial function, sine, cos, exponential function and modulus function. But please notice the last three I have specified that it is only in their, in their domain. What does that mean? For tan, what do you have to do? You have to remove all those points for which cos x will be 0. That means you have to remove all the odd multiples of pi by 2. And what about for cot function? You have to remove all those values for which sine x is equal to 0, or in other words all the integral multiples of pi. Pi, 2 pi, minus 2 pi, you have to remove all of that. What about the log function? Log function is only defined for positive numbers, not for negative numbers. What about the rational functions? Remove all of that for which the denominator turns to 0. So do you see how this question is different from the ones we have done so far? Usually we check the continuity only at the points 2 or 10, wherever the break happens. But here we are going to check the continuity for every real number. We are going to check how f behaves on the whole of the real number line. So we will start with what we know. We will check the continuity at the point 2 and then at the point 10, and we will see what happens. So what is happening at 2? So at 2, go for the one where you see x less than or equal to or greater than or equal to. Here it is strictly greater than. So go for the one which has the equal to sign. It is f. At 2, the value of f is 5. What about the values less than 2? Here you see it is 5. Wherever you see x, you substitute 2, but there is no x. It is a constant function, so it is f. Now go for f from the values which are greater than 2. So what do you have here? Between 2 and 10, the value is 2x plus 1. So instead of x, you substitute 2 and your answer is 5. So what do you see? Whether you come from values less than 2 or from values greater than 2 or at 2. In all of this, the value is 5. Or in other words, the function is continuous at 2. Now check for 10. At 10, what happens? Here is where you have the equal to sign. At 10, it is 21. And when you come from values less than 10, here you have. Put 10 here. 2x plus 1, that becomes 21. And then for values greater than 10, you have here, it is again 21. So at 10, wherever you come from the left or from the right or at 10, your answer will be 21. So what do you see? There occurs a break once at 2 here and then once at 10. And we have found that at 2 and at 10, the function is continuous. But then there is still a lot of real numbers here, right? So what happens when x is less than 2? You see that it is a constant function. And what did we learn? Constant functions are continuous. So here also it is continuous. And what happens between 2 and 10? It is 2x plus 1, which is a polynomial. Polynomial functions are continuous. So here also it is continuous. What happens after 10? It is 21, which is a constant function. Constant functions are continuous. So here also it is continuous. So what have we proved? Using the properties and the examples of continuous functions, we have proved that over the whole of the real line, it is continuous. Now we go on to the next question. We have to discuss the continuity of this function. We have to check whether this function is continuous for any real number. And there is a lazy way and there is a proper way of doing it. The lazy way, of course, is we are just going to use the properties of continuous functions. We are just going to express this f as a composition or as a sum or a product of continuous functions. We will first do that. That will be the easier one to do. You have a modulus function here, right? So take the modulus function as say h. And then you have something inside also, right? That, let it be gx. Whatever comes inside, 1 minus x plus modulus of x. So now, what is f of x? F of x, if you check, you have first taken a gx and then you have applied h on it. So, it is h composition g, right? You take g, they have taken g and then they have applied the modulus on it. So, this is actually h composition g. But what do you see about h? It is a modulus function. Modulus functions are continuous. So h is continuous. What do you see about gx? It is the sum of two functions. What are those functions? One is 1 minus x, which is a polynomial. So it is continuous. The other is modulus of x. Modulus functions are continuous. So you have taken gx as the sum of two continuous functions. So gx is also continuous and the composition of two continuous functions is again continuous. So fx is continuous. This is the lazy way. You just apply the properties. Now we can do it the other way also. Let us try that way. Whenever you see modulus, always remember you have to split it into two. Wherever, suppose you have modulus of x plus 1, then how do you split it? Split it into two. One part where x plus 1 is less than 0, the other part where x plus 1 is greater than 0. Always split it like this. Here your modulus, what is coming inside the modulus? It is 1 minus x plus mod x. So take mod x is, first take it is greater than 0. For the second one, take if it is less than 0. What happens if it is greater than 0? Then this modulus of x is just what? It is just x. So here it is 1. What happens if for all the negative x? For all the negative x, it is negative. So here it is 1 minus 2x. Now what do you have? You have a function which is split at 0. What happens before 0? Whenever your x comes less than 0, to the left of 0, you see it is a polynomial. Polynomial functions are continuous. So this is continuous. What happens when it is greater than 0? It is a constant function. Constant functions are continuous. So after 0 also continuous. Before 0 also continuous. All you have to do is check the continuity at 0. If your function is say passing like this, before and after 0 it is continuous. We just want to make sure that at 0 it is not experiencing a break. That is all that is left to prove. So what do? Check the value at 0. It is 1. Check the value to the left of 0. Before 0 it is what? It is 1 minus 2x. Putting x is equal to 0, it is what? It is 1. Then come from values, this is the left hand limit and this is the right hand limit, and come values which are greater than 0, your value is 1. So what? At 0 it is 1, less than 0 it is 1, greater than 0 it is 1, or in other words, it is continuous. When it passes over 0, it is continuous. It does not experience a break, or in other words, throughout the real line, fx is continuous. We have to check the continuity of this function fx. We have to check whether it is continuous for any real number you take. There is a modulus here. It is always better to get rid of it and write it in the proper way. Now take f for all values less than 0. For all values less than 0, what will be modulus of x? It will be minus x. So this will be what? X minus minus x, 2x by x. So your value will be 2. And at 0 what happens? At 0 it is 2. What happens when it is greater than 0? If it is greater than 0, then your x will be positive. So x minus x by x, that is 0 by x, that means it is 0. So just one look at it, you know this is not going to work. Why? Because when you come from values less than 0, you have 2. At 0 you have 2. But then when for all values greater than 0, you have 0. Which means what? The limit itself does not exist. F of 0 is 2. Its left hand limit is what? Again 2. But its right hand limit is 0. Which means the limit does not exist. So it is not continuous at 0. But then what about before and after 0? So if for all the values less than 0, it is 2. Constant function, continuous. For all values greater than 0, it is what? 0. Constant function, continuous. So this function is continuous for the whole of the real number except at the point 0. Now what do you have? The limit does not exist. But then did you notice the left hand limit? And at 0 it is same. So at 0 and before 0 you have the same value. That is why I have shaded this point. But then after that, the right hand limit, it is completely disjoint, or in other words, it's a jump discontinuity. We have to find the value of a and b if your f is continuous at 4. That means to the left of 4, to the right of 4, and at 4 you will have the same value. But you see here modulus, just first get rid of modulus. For x less than or equal to 4, what do you have? X minus 4 is less than or equal to 0. I have just subtracted 4 throughout the inequality. So x minus 4 is less than 0. That means what? It is negative. So therefore modulus of x minus 4 will be what? Negative of this. It will be minus x minus 4. So x minus 4 by minus of x minus 4. That means what? The whole of the first term just gets reduced to minus 1 plus a. Now, at x is equal to 4, we know it is a plus b. What happens when x is greater than 4? Continue the same way. If x is greater than 4, then subtract throughout with 4, then you get x minus 4 is positive. That means what? Modulus of x minus 4 is just x minus 4. So x minus 4 by modulus of x minus 4, which is x minus 4. So your answer is this. So we have got rid of all the modulus and got such a neat function. Now what do we see? It is continuous at f. So that means whether you come from the left of 4 or at 4 or to the right of 4, your value will be same. So from this, what do you get? Subtracting throughout with a, what do you get? You get b is equal to minus 1. Here subtracting throughout by b, what do you get? A is equal to 1. With an example, we will see how the continuity or the discontinuity is affected when you take a composition of a function with itself. So look at this function, f of x is 1 by x minus 1. The minute you see that, what should you know? 1 cannot be a point in the domain. 1 just cannot be there. You have to remove 1. But then once you remove 1, what happens? What happens to the left of 1? You have 1 by x minus 1. X minus 1 is a polynomial function. So its inverse, x minus 1 is a polynomial function. Polynomial functions are continuous and inverse of continuous functions are continuous. So it is continuous in this area. What happens to the right of 1? Again, inverse of a continuous function, continuous. So to the left and to the right it is continuous. But then when it passes through 1, it experiences a break. It experiences a discontinuity. So what do you have? F will be continuous on the whole of the real number line except for 1. Remove 1 and then we are fine. Now you go to f composition f. That is what you need. For composition of any two functions, any f and g. Suppose f goes from a to b, g goes from b to c. Then g composition f will go from a to c. Not f composition g. Remember, g composition f will go from a to c. So now here we do not have two different functions, right? We have just one function. So what has happened? You start with the same domain. Now you have already lost a 1. Let us see what else we are going to lose. Now f composition f of x is what? Wherever you see x, you substitute it with 1 by x minus 1. Here you have your x. Instead of that x, put 1 by x minus 1. Then you get this. The minute you see that, what should you know? It cannot be continuous on x is equal to 2. It cannot be there. It has to be removed. Why is that? Because this function cannot be defined at x is equal to 2. It tends towards infinity. So we have already removed a 1. Now you remove a 2 also. So, except for these 2 points. What happens before and after that? So before of 2, what happens? It is a rational function. After 2 also it is a rational function. It is fine. But when it passes through 2, it cannot be continuous. Because why? It is not defined. Now you know that it is not continuous at 1 and 2. You don't have to worry about it. But in case you are curious to know what happens to the limit, this is what happens. It's interesting to know, right? It is interesting to know what is happening. So here you have a break at 2. Before 2. Or to the left of 2, take x is equal to 2 minus h. To the right, take 2 plus h. So instead of x tends to 2 from the left, we can take h is equal to 0. Here also we can take h approaches 0. So what does this whole thing become? So instead of x approaches 2 from the left, we get this. Wherever you see x here, put 2 minus h. For the right hand limit, wherever you see x, put 2 plus h. 2 minus h here, 2 plus h here. You will see this one is 1 by h minus 1. As h tends to 0, you will see that 1 by h tends to infinity. That is your left limit. What happens to your right hand limit? Your right hand limit also, this is what happens. Wherever you see x, put 2 plus h. You will see that it is minus 1 by h. So as h tends to 0, this whole thing tends to minus infinity. So the right hand limit tends to minus infinity, is known as infinite discontinuity. So this is the example for that. With this we come to the end of this class. This is your last question, so I have a request. At this point, pause the video, try to solve this question yourself. Find the value of a and b. It is given that f is continuous in this interval 0 to pi. So do the question yourself and just double check the answer with me so that you know where you are going wrong. Hopefully you will not go wrong, but if there is any mistake you can correct it. So just pause the video here and do the question yourself. Now what do you see? You have two splits in the number line. The first one happens at pi by 4. Then what will you get? You will get three values. One from left, one from right, and one at pi. So combine all the three, get one equation. Then the other split happens at pi by 2. Again you will get three sets of values. One from left, one from right, one at pi by 2. Join all of them to get one equation. Shall we do now? So when you come from this, from values less than pi by 4, what do you get? Put pi by 4 here. Here you get a pi by 4. Sine pi by 4 is what? Sine 45 is 1 by root 2. It gets cancelled. So your whole term now reduces to a plus pi by 4. This is less than or equal to, right? So at pi by 4 also you have the same value. Now what for values greater than pi by 4? Here put cot pi by 4, it is 1. So here pi by 4 it will reduce to pi by 2. Your value will be pi by 2 plus b. So combine all these three values, you will get an equation which looks like this. It is pi by 2 plus b, that means a minus b is equal to pi by 4. This is your first set of equations. Now with this over, the pi by 4 part over, we move on to the pi by 2 part. And an important word of caution, do not continue with this value. Why is that? This was a different value. This is only for values pi by 4. How does it behave at pi by 4 when it comes from its right side? That was what this value for. In both these equations you have substituted pi by 4 because their break happened at pi by 4. But then look at this one. Where is this break happening? The next break is happening at pi by 2. So now you have to substitute this middle value, whatever value comes here. Now put pi by 2 here. So do not start with the same value and continue. This is something different. This is how the function f behaves when it comes from the values greater than pi by 4. So now you are dealing with pi by 2. So see here, pi by 2. How does it behave from when it comes from the values less than pi by 2? Here put pi by 2, here put pi by 2. If you put pi by 2, what will you get? Cot pi by 2 is actually 0. Cot 90 is actually 0 because cos 90 is 0. So cot 90 becomes 0. This whole thing becomes b. This is less than or equal to. So at pi by 2 also the same value. And what happens here? Here cos pi is what? 2. 2 into pi by 2 will be cos pi. So this will become minus a minus b. So now equating all of this, what will you get? You will get this. That means minus a is equal to 2b. This is your second set of equations. Now all you have to do is substitute it here. Then what will you get? You will get b is equal to minus pi by 12. And a will be equal to pi by 6. So that is it. With this we come to the end of this lesson. Till I meet you next time, you stay safe. Assalamu alaikum.